Alright, so in this particular topic, we're going to start moving from one-dimensional motion into two- or three-dimensional motion. We're mostly going to focus on two-dimensional motion because we can learn the concepts that we need to learn without adding the complication of a third dimension, especially since it's difficult to draw it on a board that's only two-dimensional. So the first thing we need to do is discuss position. Because we're used to position being either in the x direction or in the y direction. Now we're going to talk about a combination of both. And so we use a vector that encompasses all three dimensions essentially, where we're going to have a vector r is equal to our x component, which would be in the x hat direction, the y component, which would be in the y direction, and the z component, which would be in the z direction. And so from the individual components, we could use Pythagorean's theorem, which we can use also for three dimensions, in order to find the magnitude of that particular vector. And finding direction is a little bit more complicated in this concept, which is one of the reasons why we typically just work in two dimensions, because essentially you need two angles then to express. So you can get in between the x, y, and z axis and get that vector in the three-dimensional space. So this gives you, if you think about, you would have some origin that would be 0, and you would have a vector r that points off into space. And then the object would move, and it might be over here, and so your change in r would be essentially how much it moved. So this would be r initial, this would be r final. This is then going to allow you to calculate average velocity. You can tell I've been teaching physics too long because I have trouble writing capital A's rather than deltas. Because your average velocity is then going to equal that delta r over the change in time. You can also find your average velocity for three-dimensional motion if you have the individual positions function. So if you have x as a function of time, y as a function of time, and z as a function of time. So what you would do is you would take your x as a function of time and plug in your two times so that you can find delta x, and then divide by the change in time, and that would give you your x component. And then you can do the same thing in the y direction, plug in to the y position function time, do the subtraction, and then divide by the change in time, and that would give you your y component. And then the same thing in the z direction, where you would take your z position function, plug in time, do your final z minus your initial z, then divide by the change in time, and that would give you your z component. So you would end up with an x component, a y component, and then a z component to your velocity, which then you would need to actually find magnitude, use Pythagorean's theorem. Alright, so progressing on, what happens if we want to find, instead of an average velocity, an instantaneous velocity? Alright, so remember, when we want to find an instantaneous, that means we need to take a derivative. So in this case, our velocity as a function of t is going to equal the derivative of our r vector, so our position vector that encompasses both the x, the y, and the z direction. And that r vector is, sometimes we put things in terms of the radial direction, where it's just r as a function of t. And you'll see some examples of that as we progress through the semester, where rather than trying to deal with the x and y separately, it's just some radial distance r from a center point. And that's going to be very useful when we do things like orbital dynamics. Right now, though, we've been doing a lot of stuff with x and y. So what this r vector is actually going to look like is you'll have let me write this off to the side here. You'll have some x as a function of t in the x hat direction, plus y as a function of t in the y hat direction, plus z as a function of t in the z hat direction. So you'll have individual functions that describe how the motion changes in the x, the y, and the z direction. And what that means is that you're going to have to take a lot of derivatives, because it's going to separate out into taking the derivative of the x position function in terms of t, and that's going to give you your x component, and you're going to have to take the derivative of the y position function in terms of t, and that's going to give you a y component, and then you're going to have to take the derivative of the z direction in terms of t, and that's going to give you your z component. You see why we tend to focus on just the x and y direction, because how many times do you want to have to take 3 derivatives in a row? And once again, that then is going to give you a velocity in the x, a velocity in the y, and then a velocity in the z direction. So if you want to find velocity, and not just the individual components, once again you have to use Pythagorean's theorem. Very similar to what you would have done up here in the average velocity section. Alright, so we can look at a similar concept for acceleration, where if you have a velocity in the x direction as a function of time, the first derivative would give you the acceleration in the x direction. And then very similar in the y, you have a velocity function in the y direction in terms of time. And then finally, if you have a velocity in the z direction in terms of time, you could take the first derivative and get the z component of the acceleration. So at that point in time, you would have an x component of the acceleration, a y component of the acceleration, and a z component of the acceleration. And once again, you'd have to use Pythagorean's theorem to find the magnitude of that particular acceleration. And then you can use inverse tangent to find position, but as I said, that gets complicated for 3 dimensions. So typically, if I want you to find a direction, I'm going to stick to 2 dimensions. I also want to point out that you can get acceleration from position function by taking the second derivative. But once again, you're going to get an x component, a y component, and a z component based upon what direction that object is changing position in.